Hello, everybody, and welcome to Unit 3, 3.2, the life cycle of stars, where we're going to talk about the birth and death of stars. We'll start off with the birth. A nebula, or in this case, the first use with the letter E at the end is nebulae. Nebula is a huge cloud of dust and gas in space. What you'll see on the right there is a brand new picture from the James Webb Telescope showing the pillars of creation. This is a nebula where the gravity of gas and dust pulls everything inwards, and small cores of material will accrete and have more gravity, and they will continue to accrete and accrete until they get bigger and bigger, and eventually they can move on to the protostar phase. A protostar is when you get enough material that the cores get large enough to smash together and heat up. At this point, you have something that's like a star but not quite a star yet. When there's enough gas and dust, nuclear fusion will begin. Stellar ignition is the point where fusion causes the star to shine, and that's when you go from being a protostar into a star. Again, this picture is from the James Webb Telescope. This is a new image from the new telescope that was put up just this past year. Okay, when we're talking about the life cycle of stars, there are two main general options. There's the average size star, which is what most stars are, something like our sun, or a little smaller, or just a little bit bigger. It will generally turn into a red giant, then it will blow off the outer layers, turn into a nebula, and wind up as a white dwarf. If something is bigger, depending upon how much bigger, it will turn into a red giant, undergo supernova, where it blows off the outer layers very violently, and depending upon its size, it could turn into a neutron star or possibly a black hole. So we'll start off with the average star life cycle. Most stars are average stars. The smaller the star, the larger its life, or the longer its life, because it will burn its material much more slowly. Larger stars use up the fuel much more quickly. Most stars can live billions, and it's possible trillions of years. Most of this time they will be in the main sequence, and if you look over here, you will see this band. That is the main sequence, and you can see that they go from red up to yellow, white, and eventually blue, and that's based on their temperature. Now, the main sequence stars are fusing mostly hydrogen into helium. 90% of their life will be spent in the main sequence. The sun is about 5 billion years old, and it's assumed to be about halfway through its lifespan based on how much hydrogen it's used up. The mass of the star will determine its length of time on the main sequence. Now, there's something called hydrostatic equilibrium. So what happens is gravity is pulling things together, and it tries to collapse the star. There's an outward pressure caused by fusion. All these atoms that are hitting each other, they actually push outwards. And what happens is the star hits an equilibrium, or a balance. If something lowers the outward pressure, so for some reason it's not being pushed inwards, the star contracts and will be smushed in until a new equilibrium is established. The same as if it expands, the same thing will happen. If the star starts to run out of fuel, it will start to expand. Now, the death of an average star close to the size of the sun, so this would be something that would theoretically happen to our sun. It will swell as it runs out of hydrogen. Our star could swell up to the point where it will consume Mercury and Venus and possibly the Earth. That's how big it will get. It will become a red giant. The outer layers of hot gas will eventually expand away and just kind of blow away from the star. That turns into something called a planetary nebula, even though planetary nebula has nothing to do with planets. The core will collapse into a white dwarf, and the white dwarf will slowly cool over time, and eventually when it cools off enough, it will turn into a black dwarf. There will be no more fusion. It will not be putting out any more light. And if you look at this picture, somewhere here in the middle is a small white dwarf, and this is the planetary nebula expanding away. Now, if you get something that's bigger than the sun, so quite a bit more massive, and these numbers are subjective a little bit. 7 to 20 is an approximation. So 7 to 20 times more massive than the sun. When it runs out of hydrogen, it will start to fuse heavier elements. Iron is the heaviest element that can be formed through fusion. You can't form any of the heavier elements through fusion. The heavy elements up through iron will build up in the core. Running out of fuel, it will swell into a super red giant, so much larger than what the sun would turn into. gravity will cause the outer layers to be pulled into the core. So eventually gravity will try and establish a new hydrostatic equilibrium and pull everything in. And what will happen is, as it pulls everything in, it'll just keep accelerating towards the center. And everything will smash into the middle really hard. And what will happen is the outer layers will expand violently outwards. They rebound outwards at a high speed, and it'll appear to be like an explosion. The outer layers blow off really fast, and the inside core stays. This is referred to as a supernova, the most common one being a type 2 supernova, also known as a core collapse. The explosion will actually create heavier iron or elements than iron, because now you have much more pressure, much higher fusion, and it will create these heavier elements. The hot gases that have blown off will expand, and all that will be left is a neutron star. So here's a remnant of a supernova. Somewhere in here, there is all that's left, a neutron star somewhere in the middle, and these are the outer layers that have blown away. And this is expanded a long way, light years away from the center. Now, what happens if you have an even larger star, something even more massive, so more than 20 times massive than the sun? Well, then you get something else. Like smaller stars, it will burn all its hydrogen. Then it will fuse its heavier elements up through iron. Then it will swell to a red supergiant, just like in the smaller ones. But this time, the one thing that's different is when the collapse starts and everything starts to smash inwards, it will overcome, the gravity will overcome any outward pressure, and it will continue to implode to a point of incredible gravity. And this outward force cannot push back enough. That collapse never ends, and it essentially turns into a black hole where everything has sucked itself inwards, and it just keeps sucking inwards. It just keeps collapsing. Gravity keeps pulling inward. And what you get, like I said, is the black hole. That's all that's left. There is nothing left of that particular star. And we'll talk a little bit more about black holes in the next section. And here is a picture of a couple different types of black holes. Here you have a pretty large black hole. I mean, here's the sun's diameter, and then this is Mercury's orbit. So this is pretty big. Here you have something much more massive. This is Pluto's orbit. That's well beyond Neptune. And this black hole is beyond that. It is a massive black hole. It is extremely large. And that is it for this presentation.